Hello, everyone. I'm Lucas Silber, presenting with Irene Yoon, our presentation, Equational Proofs of Optimizations with Interaction Trees. So the goal of the work we're presenting is to create a framework for writing proofs of correctness for program transformations, where the programs are from effectful languages and the proofs are compositional. Our main tool for accomplishing this is the interaction trees library. Interaction trees are a co-inductive data structure in Coq that are useful for modeling programs. In particular, we use them to model effectful and possibly divergent programs. They are easy to work with because they have a rich equational theory that we formalize in Coq and provided in the library. So now we can look at what the actual structure of interaction trees are. So first we've got leaf nodes or return nodes that just return pure values like R. We've also got tau nodes that represent a silent step of computation, and uninterpreted visible event nodes, which include an uninterpreted event E and a continuation K. Intuitively, we imagine that E is being passed off to some environment, which then interprets it and returns a value which the continuation gets run on. Here's an example computation, which takes a few silent steps of computation, then gets a global state variable, checks if it's even, then sets the variable to n+1, and then returns the original value. And if it's odd, it just goes into an infinite loop that silently diverges. So here we can see a diagram of how we represent program semantics using iTrees. We start with the program syntax. Then we denote this program syntax into uninterpreted iTrees, where now we can compare them using a relation known as weak by simulation. And then we interpret these iTrees into the semantic domain, which has its own notion of equivalence. And the way that we actually implement this denotation phase is that we recurse on the program syntax, and then we have interaction tree combinators for various program control flow operators. So first, let's look at what we have for sequential composition. So here's our old computation that we use as an example. We're going to call it T1. Suppose we have another computation T2. This one's parameterized on some value X, which doesn't do anything all that interesting. And we want to compose T1 and T2. Well, how we do that is we take all of the leaves of T1 and then replace them with T2 with X specialized to the return value. So you see how that works here. We have other combinators. In addition to sequential composition, we also have a loop combinator, which takes in a body and an initial value. You see a diagram of that in the bottom right. First, the initial value is fed into the body, which then produces either a loop signal that has a continuation value it feeds back in, or a halt signal that contains a return value that the entire computation returns to. We also have a mutual recursion combinator, MREC, which we're not really going to go into, and all of this is implemented as Coq code. So let's get back to this weak by simulation relation I mentioned earlier. So here's a pictorial idea of how it's defined. So first, if you have two leaf nodes that return the same value, they're weakly bisimilar. Then if you've got some taus and bisimilar trees, you can either freely remove a finite number of taus from either side, or you can remove an unbounded, possibly infinite number of taus as long as they match on both sides. This is important because otherwise we might end up relating infinite, silently diverging computations to other different computations. My apologies. And then we have the viz case, and two visible event nodes are weakly bisimilar if they contain the same event and their continuations are pointwise bisimilar. So given any fixed value, they return bisimilar results. So now that we have this notion of equivalence, we can start talking about our equational theory. So these first couple of equations are also known as the monad laws. The first two correspond to the fact that ret is an identity when it comes to sequential composition, and this third one corresponds to the fact that sequential composition is associative. So now that we've talked about our combinators a bit, and we've got a sense of how denotation can work, we can move on to interpretation. So how we interpret these I-trees is we define the interpretation on the event, and then we can automatically extend that over the entire structure. The way that we do this is closely related to algebraic effects, if you're familiar with that. So now let's see how we can handle events. So suppose we have get and set again. We know what get and set should be, right? Get should return the current state, and set n should replace the current state with n. So you can see how we can pictorially represent this in the bottom. If we handle state get, we get a function that takes s and returns s both as the return value of the computation and as the state that should be threaded into future computations. And if we handle set n, we take in a state s and return n as the new state and just the unit value as the return value. So once again, when we have a handler like this, we can extend it to an interpreter over the entire interaction tree automatically. And we can do this as long as the target computation, target semantic domain can encode pure return computations, denoted ret, and sequential composition, denoted with this bind notation that we've seen a couple of times before. And how this works, we can see with these following equations. Interp always maps ret to ret. This corresponds to the fact that interp should never add effects to effectless code. And you see here, interp handles a visible event by handling the event and then binding the result to the interpretation of the continuation. With that all set, I pass the rest of the presentation off to Irene.
Hello, thank you, Lucas, for the first part. I'm Irene Yoon, and for the second part of this talk, we're going to take a look at a case study where we show how to leverage the equational reasoning framework in interaction trees to write a compositional compiler optimization proof in Coq. The compiler that we're talking about, specifically, compiles an imperative C-like language into a simple assembly language. The optimization we are interested in is performed on the assembly language level. So let's first look at the language that we're dealing with. The simple assembly language that we have at hand is ASM. At the high level, these represent control flow subgraphs that link basic blocks, which are lists of instructions that end with either a jump or a branch to another basic block. Here we can see a diagram of an example program. We have basic blocks A, B, C, and D, and as we can see here, A jumps to label B, which points to basic block B, and depending on the value stored in variable X, it may either proceed to jump on C or D. C proceeds to continue on some other basic block, and D goes back to itself. So what is the compiler optimization that we would like to have? We're going to do a peephole optimization on ASM, which is one of the most elementary compiler optimizations. The idea is that you replace equivalent sets of adjacent instructions. Examples of these would be replacing instructions that are equivalent to null sequences to no-op, for instance, if you were to load the value of A and store it back to A. You might also have a chunk of code that has redundant loads and stores. Here on the second box, we see a redundant load of a variable I on variable C, which can be removed as in the right-hand side. Another kind of people optimization that you might want to do is replacing unnecessarily expensive operations. For instance, the multiplication operator is slightly more expensive than the addition operator. So instead of having an instruction that multiplies a variable by 2, you can have it add the variable twice. This is all good and simple, but it turns out to be quite tricky when we start reasoning about the correctness of even these kind of simple optimizations. Informally, as we saw on the last slide, reasoning that the left and right-hand instructions should be semantically equivalent is intuitively fairly straightforward. But lifting this local reasoning to the context of a whole program turns out to be difficult with traditional approaches. They lack compositionality. For instance, requiring explicit invariance about the program counter. So the goal here is that it would be really nice if we can have a general lemma for people optimizations where, given some optimization that replaces an instruction to a semantically equivalent list of instructions, if you have any given program P, if you were to substitute in this optimization, the semantics of the program is preserved. The key point here is that it would be great to have composable rewriting without having to worry about control flow or program counters. In fact, all of the equational library and general data structure that iTree provides will help us achieve this. We'll talk about how this happens in the next few slides. First of all, how do we represent control flow in ASM? We saw this simple pictorial program where we have branching instructions and possible looping. We can decompose this further. Instead of thinking of this as one giant control flow graph, we can think about it instead where a program can be thought of as a circuit or diagram where wires correspond to jumps or program lengths. We decomposed here on the level of blocks where each have entry and exit labels corresponding to branches and jumps. So now that we have this decomposition, how do we recompose this again? This is where iTree combinators come in. Lucas explained various combinators that we can use, such as sequential and looping combinators. The most useful one here is the loop combinator, which allows us to iterate over a given loop body. With this, we can wire denoted blocks together with its respective entry and exit labels. This is useful because once we can represent our program structure with iTree combinators, we can leverage this structure for equational reasoning because we have all these nice equational laws. For instance, we can lift pointwise equivalence on functions. If we have two functions which are pointwise equivalent, the iteration over these two functions as loop bodies are equivalent to each other. We also have additional equational laws derived from the structure on category theoretic abstractions. One example of an iteration law is shown here. This one is quite intuitive to understand. If we're looping on a loop body F, this is semantically equivalent to executing the loop body once. And if the loop happens to continue iterating, it can continue iterating with a return value A. However, if it terminates, the loop will halt with a value B. Here, we figured out how to represent the ASM control flow using iTree combinators and saw how we can use equational laws from the iTree library to lift semantic equivalences at the instruction level up to the full program level. Now, how do we represent the semantic domain that we are interpreting our iTrees into? The important thing here is, what are the stateful effects that we're keeping track of? In the case of our ASM program, we have two kinds of states, which is a state on registers and another on heaps. When we are encoding this into iTrees, this corresponds to having two kinds of events, each on register and memory, where we can do a get and set register and load and store memory operation respectively. During interpretation, this becomes a representation of the program environment, here as a map of addresses and register locations to values. The resulting type, which is a state monad, is going to be taking a pair of register and memory into an iTree that doesn't have any meaningful event because everything has been interpreted, and where its return type is a pair of register and memory. Let's go back to the level of interpretation and see the big picture. We start from a deep embedding of the ASM language in Coq, where we have a syntactic notion of equivalence. And then we gave a representation of ASM programs with I-trees using register and memory events and loop combinator. This introduces a notion of weak by simulation and allows us to use the equational laws on our control flow operators. Finally, we give an interpretation into state monads so we can see the equivalence up to the resulting environment. Notice that these equations at the level of I-trees are preserved by interpretations at the level of the semantic domain. All this machinery allows us to state this general lemma with ease so that we can lift the equivalence on lists of instructions to whole programs. Once again, in contrast with approaches traditionally used in formally verified compilers, we do not need to introduce any invariants about notions such as program counters. And to prove that reasons about people optimizations becomes as simple as expected. Going back to this example where if we load the values into A, that's equivalent to a no-op, with the general lemma, proof about such optimization only become a matter of showing that this equation holds without having to worry about the context that it is being substituted into. Of course, such compositional results to prove optimizations through denotational semantics are well known in the literature and exists on much more complex cases. What is great with this work is that I-trees give us a fairly lightweight way to scale this approach to languages with complex features, mechanize it, and to tie the result into an interpreter. We've gone over a toy example on ASM, and this is a peek into LLVM, our verified, this is a peek into Vellum, our verified LLVM project, which has our continuing effort towards the verification of more complex compiler optimizations. Today, we had an overview of interaction trees as a powerful reasoning library for equational proofs and how we can leverage its combinators and equational laws to write a compositional compiler optimization proof. All the code that we've discussed in this talk is available on GitHub, and if you'd like to check out Vellum, our verified LLVM project using interaction trees, the link is here. Thank you.
Okay, thank you very much, Lucas and Irene. So just to remind you, you can ask questions via Slido. At the moment, we don't seem to have any. So let me just ask a general question about the approach. In the first part, I noticed that recursion was glossed over, but you do have this combinator. Could you say a bit more about its role or any difficulties that are associated with it?
Yeah, wait, so the MREC combinator, it is actually, I glossed over this a bit in the presentation that it's actually full mutual recursion. So looking again, the syntax I gave might have been wrong. I haven't looked at that part in a little while. If I recall, it wasn't much more difficult to implement than iter, because both of them are basically about just passing along control flow, adding the right constructors so that the Coq syntactic conduction checker doesn't get mad at you. You know, if Yannick or Steve had worked, or Irene, if you've worked on it,
sure,
MREC more, you could probably add much more to that.
One important comment. So Lucas is right that as far as definitions are concerned, the general mutually recursive combinator is not that much harder to implement than the terminal recursive one, so this iteration. The main difference is that with iter, you are always granted to get nice compositionality results. With MREC, you can actually express arbitrary recursion, But if you try to model higher order recursion, thanks to it, you are likely to lose the compositionality of the result, because basically you are forced to pass some information about the computation that you only get at runtime as an argument of your event. And if you do that, then you lose basically the compositionality that you get otherwise. So in this sense, it's more powerful, but it can get harder to reason about.
Okay, thanks. So at the very end, you mentioned LLVM. So what is the dream for the project? Which architectures, compilers would you like to verify eventually?
I guess I can handle this one. This is Steve Zdanswick. Maybe I'll turn on my video. Yeah, so we've been working on verified LLVM compiler semantics for a while. We had a project almost 10 years ago now where we built a sort of prototype in Coq and I would say that the motivation of the project is actually quite similar to what we heard in the previous talk. So verified program transformations, optimizations. We have in the past looked at verifying mem to reg and some of these similar kinds of optimizations. I think this new line of work about using interaction trees is to make that much more modular and easier to maintain over time, so that we could build eventually certified backends, but initially focusing purely at the LLVM IR and its kind of self-to-self translation. So unfortunately, the LLVM semantics has gotten a lot more complicated in the last 10 years, and it has a lot of semantic quirks having to do with things like undefined behaviors and undef and poison and complicated memory models and things like that. So what we're trying to do is to build a formal Coq infrastructure that lets us modularly reason about LLVM code. And I guess I found the last talk quite inspiring, because I think that we could use the semantics that we're building to do a verified validators. So in exactly the same way, you could use the semantics of our Vellum LLVM IR to give the justification for the correctness of program transformations. So that's kind of what we're aiming for.
Okay, great. Thank you. And can you talk about any limitations of the approach? Are there things you will not be able to certify?
Well, I think at the moment the biggest limitation is we haven't done a lot with concurrency, and of course there's a lot of, if you get to realistic, say, memory models for modern computer architectures, there's a lot of subtleties with relaxed memory models and concurrency and so on. We have dabbled a little bit, not at the scale of LLVM, in modeling concurrent computations with iTrees, but I think that's probably the biggest open challenge.
Okay.
I guess, Yannick, you could interject if you have any other thoughts about what's challenging.
No, I agree. I think on the midterm, we also have many technical questions to be able to scale to complex transformation. In particular, when your transformation will change, typically the scopes of variables, we are thinking about what is the right story to get good result, to get compositional results when your compositionality requires a stronger relation than the kind of generic by simulations that we have here. So there are midterm challenges, but I agree with Steve that the real long-term challenge that